We see in last class that introduction to post-silicon validation and what is post-silicon validation and role in the design cycle of the post-silicon validation and what are the challenges, what are the industry trends in the post-silicon validation, what is PVT characterization, how we will do the IP level of validation, that things we have seen in the last class. So today we are going to see the IP level of validation that are low speed and high speed. So firstly, to understand the IP level of validation, we should understand to understand it first we have to understand the cables. What are the cables we are using? What are the probes we are using? So basically there will be of different types of cables and probes. Different signals will require different types of cables based on their frequency handling capability. So if we select the wrong selection of the cable, it will leads to the noise pickup, signal distortion, and incorrect measurement. So we need to select the correct cable for doing the IP level of validation. So here are some idea on the cables. Like this, if you see, this is the banana cable, this is the bark cable, and you will have the bullseye cable, BNC cable, SMA cables. And if you are seeing the probes in oscilloscope, we will be having the passive and differential probe. So in depth, I'll explain you about this probes, an idea, and then we will move to the IP level of understanding. So first, banana cables is nothing but it will be like used for DC and low frequency signals. And if you see that one end of the banana cable, it will be having some plug of 4 millimeter. Like you can directly plug it in onto the validation board. But there won't be any impedance control mechanism in banana cable. And it is used where the power supply connections, like as I told yesterday, we'll be having 2 channel and 3 channel power supply. For connecting that power supply on the board, we will use that banana cable. And later, if we see the bark cable, it is nothing but if you see Arduino or Raspberry Pi or HTM board, you will connect that microcontroller with these bark cables, right? So it is similar to that. It is a multi-pin connector where based on the application and validation we connect. For example, for digital interfaces like GPI or JTAG, we use this bark cable. It is used for debugging and logic connections inside the board for checking that. And coming to the bullseye. Bullseye is one special type of cables or connector used for the high-speed interfaces. And coming to the PNC cable, it's a coaxial cable with a controlled impedance of 50 ohms and 75 ohms. uh, Impedance matching condition should be will be there. Like the impedance, cable impedance, and the system impedance should match. If it is not matching, then we can see the reflections of the signal and other violations. So we will use the BNC cable. Like if you see the oscilloscope connection, to connect that oscilloscope, we'll be having that BNC cable. It is a medium to high frequency signal. And SMA cable, it will be also similar to BNC, high frequency, and it will be having low loss. High speed signals will use SMA cable. Like if you are using any vector network analyzer, at that time we will use that cable. And coming to the oscilloscope probes, like we'll be having the passive probe and differential probe. Passive probe is a low speed. For low speed IPs, we will use that passive probe because that bandwidth will be from 100 to 300 megahertz, where the signal bandwidth of low speed also will be in between that. And we'll be having the high capacitance. And here in this passive probes, we can do the validation of I2C, SPI, GPIO. Coming to the differential probe, which are used for high speed IP validation. It measures the difference between the two signals and it eliminates the noise and other parameters. So we'll use differential probes. And it will have the low capacitance, high bandwidth, and high CMRR rate. And it is used for LVDS signals and DDR, PCI, and SGMII Aurora type of high-speed applications will use that differential probes. And if you want to see the quick summary of the passive probes and differential probe, signal type in the passive probe is single-ended, and signal type in the differential probe is differential. And bandwidth, coming to the bandwidth, passive probes will have the low to medium bandwidth, like 100 to 300 megahertz. And coming to the differential probes, it will be having the high bandwidth, which will be in sort of gigahertz. And loading effect is high in the passive and low in the differential probes. And coming to the accuracy for low speed IPs, we are not that much it is not that much difficult to see that signal and other things, so it will be accuracy will be good moderate in the low speed when we using the passive probe. And when we are using the differential probe, we use it for high speed for the accuracy. And coming to the use case, as I said, passive probes are used for low speed and differential probes are used for high speed. If you will get one doubt, like if I use the uh, high speed passive probe, what will happen? Like at that time, we can see the signal attenuation and all the losses. So we should use the correct probes for the correct validation of the low speed or high speed IPs. And coming to the IP level, we will be seeing the I2C. I2C is nothing but inter-integrated circuit. It's like a master and slave protocol. It requires two wires, STA and SCL. Like it is the two signal IP, right? STA means data and SCL is a clock. And it supports the multiple devices on the same bus. Each device has a unique address, unique slave address. So it's a simple and cost effective design. So how the communication happens means we'll be having the start condition where the communication begins from communication begins, and address frame is like master select the slave device based on this address, and acknowledgement and negative acknowledgement, the slave will respond based on the master communication, the slave will respond, and data transfer happens from data moves in 8-bit packets. And stop condition. At the end of the communication, we'll use the stop condition. And data flow is like start condition, address, and read or write, and acknowledgement, data sending, acknowledgement, and stop bit. And where we use this I2C protocol for connecting to the sensors and connecting to the memory storage and real-time clock displays like LCD display, and for ADC, DAC, converters, and for that type of modules we use the I2C. And coming to the pros and cons, it is a minimal wiring. If you see the SPI will be having 4 wire. So in I2C will be only having the 2 wire, and it is easy to implement and it supports multiple devices to connect. It supports up to 128 devices to connect, and it will be having coming to the cons, it is slower than the SPI, and it is a limited distance protocol. And address, sometimes if we give any wrong address, so it will create some conflict there. So if you see this image, you'll be having an STA and SCL lines. Based on that, we will connect these multiple slaves. If you see in the start condition, STA will go from high to low. It is the start condition. And you will be having 10-bit or 7-bit of address plus read or write bit. And you will be having the acknowledgement where STA is pulling low, and data transfer happens in 8-bit packets. And you will be having the stop condition where STA goes from low to high. This is the frame format of an I2C. And as we discussed, there will be some advantages, limitations. and real time where we use this I2C. And coming to the I2C validation setup, we'll be having host PC and the host PC with the loader batch connection with the DUT where the sock is present, and we'll be having the oscilloscope, and we will be having the power supply. In this, what we will do is first we will set the voltages like 0.9 as minimum, V nominal as 1.8, V max as 3.3. With the help of the banana cable in one end, with another end, we will probe to the test points of power on the validation board. This can be seen from the schematic, and we'll be having the 20 pin JTAG here. So with that, we'll connect this slaughter patch to the PC. In the trace 32, we'll open the script to be run, and we'll be having the prodigy. This is the key element in the low speed validation. Like we'll be having one prodigy equipment. In that, we can make the prodigy master or slave, and another is we can make the DUT master or slave. For example, if prodigy is a master and DUT is a slave, we'll send some bits of data, 8 bit of data, and we will check whether that DUT received or not. In the same way, we can make the DUT as master and prodigy as a slave, so that we can functionally check whether that I2C protocol is working or not. And coming to the and we can see the corresponding signals in the oscilloscope. Here we will be using the passive probes as it's an low speed IP. And coming to the SPI, it's a serial peripheral interface. It's a synchronous communication where the clock, as we use the clock, and it is used for short distance communication between master and slave devices. And it's very high speed compared to the I2C. It is a full duplex communication because we'll be having MOSI and MISO lines, right? So we can data flow can be from both the directions simultaneously. And it's a simple protocol with minimal overhead. And it's a more reliable data transfer. We'll be having the four main signals in the SPI that are MOSI, master out slave in, master sends data to slave, and MISO where data master in slave out, where slave sends data to master. So for this application only, we will use the prodigy. And coming to the clock is always generated by the master. And coming to the SS or CS, slave select or chip select selects the slave device to be communicated. And communication flows will be like master select the slave using the slave select, and clock signal starts, and data is exchanged simultaneously from master to slave and slave to master, and communication stops when slave select goes high. Data transfer concept, master to slave continue simultaneously data exchange will happen. Coming to the advantages, it's a very high speed protocol compared to I2C, and it's a full duplex communication, whereas I2C is a half duplex communication, and it's no addressing is required. Like in I2C, we will be giving the slave address, where in SPI we are not giving any slave address. We will be directly selecting the slave, and it requires more wire. Coming to the disadvantages, it requires more wires than I2C, and no built-in acknowledgement is not there. Acknowledgement bit won't be there here, and you can see visually through this image how it will look and how the communication will be there. Coming to the SPI validation setup, same way to the I2C, we will be having one DUT where SOC is there present in the socket, and we'll be having the power supply using banana cables. We'll keep that V minimum, V nominal, and V max voltages in the board, and we'll be having lotter batch where we can select master and slave, and we'll be having trace 32, and we'll be having the oscilloscope with passive probes. Same way we can make, for example, if we make prodigy as master and DUT as slave, we'll initiate 8 bits of data transfer and we will see 8-bit data is received correctly or not. And coming to the JTAG. JTAG will be having the 4 signals like TDI, data in, data out, clock, and test mode select pins. So I'll explain you the validation setup of that JTAG. In JTAG, we'll be having a host PC and loader batch. In SOC, we'll be having the 20-pin JTAG here. In the 20-pin JTAG, we'll be backside of that, we will be doing some soldering to make sure that 4 pins are connected to the 4 channels of the oscilloscope of high bandwidth of 25 gigahertz. And we'll be having the power supply as usual. Using banana cables, we'll keep that power supply. And we will see the corresponding signals in the oscilloscope. And like you'll be having where with this JTAG is used, it is for chip debugging, boundary scan, firmware flashing, and board testing. This is the JTAG validation setup. If you see, you'll be having host PC, loader batch connection. Back of it, we'll be soldering that 4 pins of 20-pin JTAG to the oscilloscope. And when we run the script in the Trace32, we will be seeing the corresponding signals of JTAG, TDI, TMS, T clock, TD out in the oscilloscope. And we will be giving the power supply to this board. And coming to the SGMI, which is an high-speed IP, SGMI is nothing but serial gigabit media independent interface. It's an high-speed serial interface used to connect the Ethernet MAC with Ethernet 5. So to convert it's under the IEEE standard of 802.3. And it convert the parallel data to serial and serial stream to parallel stream. And why SGMI is used is, in earlier we'll be having the GMI, Gigabit Media Independent Interface, where we'll be having almost 24 pins. So pin wise the count is more. To reduce that pin count, we are using the differential pair. Like in SGMI, we'll be having TXP, TXN, RXP, RXN, like TX positive, TXN negative, and RX positive, RXN. So it supports with help of that 4 connection, it supports a high speed communication. And it enables compact SOC design. And we can see, in data rates in SGMI are 1.25 gigabits mode. It's a default mode. It uses for different speeds like 10 megabits per second, 100 megabits per second, 1000 megabits per second Ethernet, and it uses 8 or 10 enabling encoding. The concept of encoding is like actual data will be 1 gigabits per second. Encoded line will be adding some more data to it. So it will be 1.25 gigabits per second. In same way, we will be having another mode with 3.125 gigabits per second mode, which is an high speed mode. It is used for 1000 base X. It's like fiber net application, fiber Ethernet. So it uses 8B or 10B encoding. And it is used for high bandwidth applications. It is mapped with SUDDER systems. SUDDER systems are nothing but high speed IPs. And as I told, like we'll be having the four signals like TX positive, TX negative, which are differential. Data from MAC to Phi, physical layer. We used to send the data if we are like, and we'll be having the RX positive, RX positive and RX negative, which is a differential. Data transfer happens from physical layer to MAC layer. And these clock positive, clock negative control are optional. And in SGMI, we are using an bandwidth of 125 gigahertz. 125 megahertz of clock, and we'll be having an architecture of MAC side and Phi side. In MAC side, data will be from parallel data is converted to serial conversion. In physical layer side, Phi side, we will be converting serial data to parallel conversion. Communication type is it's a full duplex and it's a point to point link. Coming to the features, it is having the low power consumption and it is a low pin count. If we see GMII, it will be having almost 24 pins. Now in this SGMI, we are using only 4 pins like TX positive, TX negative, RX positive, RX negative. And it is having a high speed serial link and it supports the full duplex communication. In-band signaling. No separate control lines are required in this protocol. Coming to the applications, we'll be having the Ethernet switches. For Ethernet switches and routers and SOC designs, data centers, networking devices, we will use this SGMI. If you see this diagram, we will understand in a simple format to understand quickly what are the signals and where it is used, its key features, signal definition, data rights, and applications we can see. Coming to the Aurora, Aurora is a lightweight and a high-speed serial communication protocol. It is developed by Xilinx. And why and where it is used, it is used to chip communication and board to board communication. Its key characteristics are it's like a point to point serial interface. It is having the high throughput, like it is having multiple gigabit its data transfer, and it is having low latency. No delay will be there in this protocol, and it is a no complex protocol stack, and it is scalable, supports multiple lanes and simple framing. Data rates Aurora support is 2 gigabits per second and 2.5 gigabits per second it supports. And coming to the encoding technique, we will be having 64B or 66B. Means actual versional data will be 64 bits and 2 bits will be header. And we will be having the Aurora architecture in TX side. User data input will be there and it accepts the data from user logic into Aurora core. Once the data is came into the Aurora core, it 64B or 66-bit encoder will convert that 64-bit data into 66-bit format for synchronization. Basically, this encoding technique is used for the synchronization. And we'll be having this scrambler, which randomizes data to maintain DC balance. To maintain the DC balance and to reduce the EMI effect, we'll use that. And coming to the framing, it organizes the encoded data into blocks for transmission. The block of data is used for transmission. And serializer means it converts the parallel data into high-speed serial stream. At receiver side, will be this here the data is serialized. Parallel data is came into the serial form. In deserialization, it converts the incoming data back to the parallel format. And the frame alignment detects the headers and the data alignment data blocks are correct. The scrambler stores the original data by reversing the scrambling. And decoder will extracts that actual 64 bits data from encoded stream. and output to the logic, user logic. Sends the recovered data to the system or application. Protocol flow will be in TX side, user data is going to encoding to the scrambling to framing to serialization, transmission. And here in receiver side, the serial data again going to deserialize, alignment, descrambling, decoding, and user data to the system. And coming to the features, it will be having the high speed communication features, and it will be having the low latency, low lightweight protocol, built-in error detection, and flow control support. If you see in this slide, we can quickly remember what is the process, what are the signals of Aurora, what are the data rates it supports, why we use the Aurora, what are its key features, what are its pros and cons, everything will be seen from here. Coming to how we will do the validation of this SGMI or Aurora. We'll be having the host PC and we'll be having the lotter batch, and on the DUT we'll be having a bullseye port. In that bullseye port, it will be usually of 8-pin bullseye port. Where will first half will be TXP, TXN, RXP, RXN. So that 4 cables with help of the differential probes we will give to the oscilloscope. And here in the 3-channel power supply, we will set the voltages like V minimum as 0.9, V nominal as 1.8, and V max as 3.3. With help of banana cables, we'll connect on this DUT. So, we'll be having some CMM script of that particular SGMI or Aurora. So, we will run that CMM script and we will see the corresponding signals, that is I diagram on the oscilloscope. I diagram on the oscilloscope. Based on the I diagram, we will see the signal quality of the I diagram of this high-speed interface protocol. I think you understood like how we will be doing that low speed, high speed setup, how we are going to connect this schematic, like where to connect that I2C, like GPIOs of I2C, SPI, JTAG, and SGMI and Aurora's bullseye connector, bullseye cable, that all we can get from the schematic of the particular board. Yeah. Yeah. Any doubts as of now? Hello?
No, you can go ahead.
Hello.
Yeah. Hello?
Hello.
Yeah.
Yeah, actually, could you explain about the JTAG connections
Yeah.
to the SOC board once again?
I'll explain.
Yeah, yeah, it's visible.
Yeah. Yeah. Coming to the JTAG, JTAG is like a joint action group protocol. Like it is used to debug the signals. And coming to the JTAG, it is like SP and I2C only. It is having the 4 main signal lines that are TDI, like test data in. And we'll be having the test mode select. And we'll be having test clock and data out. These are 4 pins. Data in pin, mode select, and clock and data out. If you want, we'll be having the reset as well, but that is an optional pin. So this is the DUT, right? This is the validation board, and inside that we'll be having the SOC. Here in end of this board, you will be having the JTAG. If you see here, this is the JTAG, 20 pin JTAG, right? Under this, we can solder the JTAG, because here in the upside, we are using that JTAG pins directly for lotter batch connection, that ribbon. So backside of that board, we'll be having the 20 pin JTAG. Using the schematic, we'll be seeing where is the TDI, where is the TMS. TDI data in and mode select and clock and data out pin. So with help of that soldering of differential probe, golden pins will be having. So using that for high different for pins after soldering, we will connect to the oscilloscope, like high bandwidth oscilloscope, like it is 25 gigahertz of oscilloscope, for example. We will connect that with the oscilloscope, and we'll be having the test script. Using the trace32, we will load that script and we will run that script. And we will see that corresponding readings of that JTAG, that signals in the JTAG on the oscilloscope. As usual, like initial, we will be setting that power supply using banana cables in this in this validation board. I think now it's a bit easy. Like we'll be identifying the 4 pins in from schematic where to solder. That soldered 4 pins are given to the oscilloscope, and we will be connecting the power on the board like using banana cable. We'll set the 3 channels voltages and we'll connect on the board. Then we will open the trace32 application and load that CMM script and run that CMM script, and we will see that corresponding signals of the JTAG. Like we'll be having 4 signals, right? That 4 signals like TDI, TMS, T clock, and TDO will be seen in the oscilloscope. And if we want, we can make a trigger option as well to display the signal in one place. We'll use one trigger option in oscilloscope. We'll keep initially like 900 millivolt like that, and we'll see that 4 signals on the screen clearly. Like that is the JTAG validation. Yeah, is it clear now? Or do
Yeah.
I need to explain JTAG
Yeah,
again?
it's clear. It's clear. Thanks.
Yeah. Yeah. Thank you. Next we will be seeing about the eye diagram. So in the SGMI and Aurora explain, right? We won't see the signals like digital signals like this. Uh, We won't see signals like this. So we will be having in this for example in JTAG we will be see a signals in such a way like TDI and other 4 clocks, other 4 pins like this the signals. But but high speed IPs like SGMI, Aurora, DDR, PCI, USB. For that we won't see signals like this. So we will do some eye diagram analysis. So eye diagram is to see the signal quality. So basically an eye diagram is like overlaps with thousands of bits on the oscilloscope, forming an like it's like visually to see it's like appears like an eye. So we call it as an eye diagram. And coming to the core parameters, in interviews they'll ask what is the eye height mean, what is the eye width will be like that. Yeah. And we will be seeing the eye height. Eye height is nothing but this is the eye height. The opening is there, right? This is the eye height. This is the eye width. So if you see like eye height is like it's an opening of an eye. It represents the noise margin. How the voltage variations can system tolerate. Like it is a logic 1 or logic 2, logic 0. And eye width. Eye width is nothing but it's an horizontal opening. That horizontal opening will tell the sampling data without any errors. And coming to the jitter. Jitter is nothing but a variation in the crossing points of the waveform. If it is a more jitter means we'll be having less timing accuracy. So the always we have to make sure the jitter will be low. and noise margin. Noise margin is defined by voltage output high minus voltage input high, and it's a high margin. And it coming to the low margin, it's like voltage input low minus voltage output low. It ensures the signal stays within the valid logic threshold, because the signal should not go into the noise margin. So it is a safer limit from higher margin to lower limit. That in that margin, the data signal should be there. Like and mass test, it's like a compliance check whether the link fails standards like DDR, PCI, USB, like that. And in interview point of view, they'll ask what is the characteristic impedance, what should be that. We should maintain the characteristic impedance always 50 ohms, because if we are not matching that, we'll see the mismatches cause that reflection, and we will see the horizontal shrink of this eye diagram due to ISI and jitter, and several mismatches can be seen due to that voltage levels and reducing the vertical opening. Frequency response, high frequency loss, dissipation, distort, raise time, fall time, blurring edges and closing the eye. Crosstalk is nothing but it's a coupling between the adjacent traces injects the unwanted signals. It will affect the vertical closure of the eye diagram. And ISI inter-symbol interface, it previous bits affect the current ones. So it will horizontally shrink. And we will see the voltage threshold like voltage output high and voltage output low, voltage input high, voltage input low. This defines the safe limits for the voltages. And we see mainly what I mean is like eye diagram, eye should be wide open so that there will be minimum jitter, minimum noise. And uh yeah, if you see this eye diagram, we will be seeing the raise time, fall time, and one voltage one level and voltage zero level, and you will be having an eye width here. That eye width is a bit period, and high height is a noise margin. If you see this much of wide open means it is having less jitter, less noise error, and eye crossings will be there. This is here, if it is crossing means it's like a jitter. And the timing margin, which horizontally it represents ISI and crosstalk. So overallly, vertically, if eye shrinks, it is due to noise. Horizontally, if the eye shrinks, it's an ISI due to the ISI effect. Can anyone tell like which eye diagram, like upper eye diagram or lower diagram, is a good eye diagram? Like the sampling and less error, less jitter, less ISI.
Upper eye diagram.
Yes, upper eye diagram is good to uh where because the eye size is big. We can see wide opening, and we are not seeing any signal overlapping here. And this vertically length is also good. Means with noise margin, noise is less. And vertically also it is having more width, which means ISA effect is not there much on this eye diagram. So by doing such type of analysis for high speed IPs like SGMII, Aurora, PCI, USB, DDR, for that type of IPs we will do signal analysis like that. This all can be seen from oscilloscope. We will run the CMM script of high speed IPs, right? At that time we will see the corresponding eye diagram for high speed IPs. Anybody have any questions?
What is CMM script?
CMM script is nothing but we will be having the test case, right? Test case is in .c file or .python file, .py file. So that corresponding file using some framework, they'll convert into CMM script, because in Trace32 we can't give directly the CMM C file. So you have to convert that corresponding C file into CMM script. And that CMM script is used to load and run the test case. In the Trace32, we can't give directly the C application. We'll be using that CMM script and running that corresponding test case.
Okay.
Yeah, if anybody have any doubts on how to see the eye diagram, for constructing the eye diagram on oscilloscope also, we'll having one procedure. I'll explain that as well. But if you have any doubts as of now, like we have seen the 5 IPs mainly, I2C, SPI, JTAG, SGMII, Aurora, and their validation setup, and how that signal will be there for low speed and high speed, how that eye diagram is there. Do you have any doubt in that?
Hello.
Yeah.
Yeah, actually, I want to know about crossover point in eye diagram.
Crossover point is nothing but that is a jitters, right?
Okay. Like, how can I analyze that crossover point?
By oscilloscope settings, we can see that crossing over points. So you understand like how much of crossing is there.
Okay.
Yeah. Anybody have any other doubt? Okay. Okay. I'll continue the next topic. Like if I'll go to one instruments, how to do the analysis of selection and how, like, I hope my screen is visible, right? Is my screen is visible?
Yes, visible.
Yeah. Coming to the instrument, lab instrument, for every IP, for every validation, that is IP level validation or wafer level testing validation or PVT characterization, oscilloscope is a mandatory skill in the post-silicon validation that everyone should do. Like everyone should understand that. So we'll be basically having the two rules to select the oscilloscope. One is the frequency rule and another one is the rise time rule. Frequency rule is bandwidth greater than or equal to 5 into the clock frequency. For example, if you are having the 5 gigahertz of clock frequency, then you have to select an bandwidth of into 5. So it will be a 25 gigahertz of bandwidth oscilloscope. And if you have an rise time rule, that will be like 0.35 by rise time. So that is the rise time rule. So if it is a clock frequency of 110 megahertz, so you will be having a 50 megahertz of bandwidth oscilloscope. If rise time is 10 nanosecond, you have to select an oscilloscope of 35 megahertz of bandwidth. So apart from that, we have to, for more accuracy, we have to check the loading and sample rate and record length. 125 gigahertz scope can safely handle low speed and high speed, as we discussed it, right? Previously, if we use for low speed IPs, high speed bandwidth oscilloscope is fine, like it's good. But for high speed IPs, if you use the low bandwidth, it will attenuate the signal and other losses or violations we have seen, right? So like that, we have to make sure we are using the right oscilloscope. And on the top of the oscilloscope, we'll be seeing three parameters. One is this oscilloscope bandwidth, another one is sample rate, third one is the data length. So sample rate is nothing but oscilloscope, how many samples per second it can take. For example, it's 100 gigasec, 100 billion samples per second it can take in 100. And it's an ultra high sample rate, ensures fine detail in capturing the fast signals and transitions. And coming to the 1 gigapoint is, it's like 1 gigapoint of memory depth. So it can store 1 billion sample points from captured waveform. So how is this signal will be stored? How much sample points it can store that signal from a captured waveform is represented by that 1 gigapoint. And this allows the recording long data without losing any resolution. And bandwidth tells you how fast the signal you can see. Sample rate will tell you how finely you can capture it, and memory depth is like how long you can store it. Three parameters are important. Like bandwidth is like how fast, like how much signal you can see using that bandwidth, and sample rate is like how many billions of samples per second you can sample the signal, and memory depth is how many how much time you can store. Like we see the sample rate, it is 100 giga samples per second. Here 1 GPT means giga points, how much time it can store, record it, how long you can record it. Here GS/S means giga samples per second. If you see the oscilloscope, right, it is 25 gigahertz bandwidth. It's a high frequency signals bandwidth used for low speed IPs as well as high speed IPs. And it is having 100 giga samples per second sample rate, which means 1000 billion samples per second it can precisely sample. And 1 GPT means gigabit memory depth it will having to store the waveform. And coming to the company model bandwidth sample rate use case, like we generally will having the Tektronix, oscilloscope, keysight infinition, and R&S oscilloscope. We'll be having 50 megahertz to 200 megahertz of bandwidth, and its sample rate will be 1 giga samples per second. And it is used for SPI I2C UART, like it is in megahertz, right? So its clock also is in megahertz. So we'll be using low speed IPs, low bandwidth oscilloscope. Coming to the Tektronix 4 series MSO, mixed signal oscilloscope, 200 megahertz to 1.5 gigahertz oscilloscope, and it is sampling rate is 6.25 giga samples per second. It's like a mid-range of validation. It is used for JTAG and other IPs. And keysight infinition will be having 200 megahertz to 1.5 to 200 megahertz to 1.5 gigahertz, and its sampling rate is 5 giga samples per second. And it is for general validation protocol analysis. And you'll be seeing keysight infusion 1 gigahertz to 6 gigahertz band with oscilloscope. It is having 20 giga samples per second. sample rate, and it is used for high speed serial validation like PCI, DDR, USB. And coming to the other high speed, other high bandwidth oscilloscope like R and H, 600 megahertz to 6 gigahertz. It is having 20 giga samples per second sample rate. And use case, it is used for advanced testing, high speed IPs. And if you see real case examples, company model Tektronix will be having bandwidth of 50 to 200 megahertz and sample rate of 1 giga samples per second, and memory depth of up to 20 kpt kpts, and memory depth of 20 kpts, and keyset is having 200 megahertz to 1.5 gigahertz, and it is sample rate is 5 giga samples per second, and it's up to 4 mpts, and R and S, it is having 600 megahertz to 6 gigahertz. It is having sampling of 20 giga samples per second, and it can go up to memory depth of 2 GPTs. And Keysight is having up to 110 gigahertz, which means sampling rate is having 256 giga samples per second, and up to memory depth is up to 2 gigabits. Yeah. Anybody have any doubts in this? How to select this oscilloscope, eye diagram, Aurora, SGMI, and JTAG, SPI, I2C, and oscilloscope probes, different passive probes or differential probes, cables, different type of cables, banana, bulb, bullseye, BNC, SMA. Any doubt in this?
Hello, ma'am.
Yeah, yeah.
In I2C, we will be having some timing diagrams now. If they'll ask in interview about the timing diagram.
Coming to the I2C interview type of questions, what they'll ask is, first they'll ask whether the I2C is synchronous communication or asynchronous communication. You can say it's as it's a clock is there, you can say it's in synchronous communication. They'll ask whether it's like they will ask you in I2C, is it a full duplex or half duplex? We can say it is a half duplex communication. And in I2C, mainly they'll ask what is the start condition, what is the data frame of that I2C, what is that stop condition. That part they'll ask in I2C.
What is the use of that? We have acknowledgement in
Yeah.
I2C. What is the
Yeah.
function of that? What it will do?
Like in I2C protocol, we'll be having the acknowledgement bit in the data frame. What it will do is, hello? Yeah.
Yeah, ma'am.
What it will do is, will be like whether the transmission data is received or not. It gives that acknowledgement to the master, like whether you received the data or the address is matched or not. After receiving one acknowledgement is there, right?
Yes.
Like it will tell that whether that slave address is correct or not, address matching or not. If it is matching, it will go to proceed to data transfer, 8-bit data transfer. Once data is received, it will say like I received the data, send next byte of data. 1 byte equal to 8 bits, right? Like it will transfer 8 bits data, right, in this protocol. So it will tell like send next data, and once data is completed, right, it will tell, okay, we can nothing data communication is completed. Like that, it will give that acknowledgement. It's a communication like from master to slave, like that acknowledgement will continue. And if it is received the correct acknowledgements, you can ensure the data transmission is correct.
Okay.
And slave stops sending messages means, then we can say that, okay, nothing data communication is happening, and stop bit will raise like from low to high. Yeah. Any other doubts in SPI I2C cables, PVT characterization, or any protocol trends challenges? Anything?
Eye diagram, how to capture actually?
Yeah, high diagram is captured using the oscilloscope. In
No.
oscilloscope, we'll be having one option like eye diagram. So we'll be selecting the type like bit error rate and other things we will see, and we'll construct the eye diagram. Eye diagram construction using the oscilloscope is having a very big procedure. So by that we can construct the eye diagram. If you want me to explain how to construct eye diagram now, I can explain that.
Yes, please explain.
Yeah. Basically, an eye diagram is set using an keysight oscilloscope, for example. And in that, we'll be taking first bit rate measurement. And if we'll take the bit rate measurement, that will be 6.25, for example, megabits per second. Later, we will use the clock recovery option, and we will calculate the exact ideal bit rate of signal that you are working with measurements. And you have to set auto scale mode in the oscilloscope and analyze that feature, real-time eye clock recovery data rate. And you will see that signal you are working is semi-automatic. And you will be manually doing that extract idea bit rate that you want to work. And in nominal data rate, you have to mention the bit rate measurement which we have taken 6.23 megabits per second. In that method, we'll be having constant frequency, first order PLL, second order PLL, like that. So we'll be generally selecting that constant frequency mode, and this allows to see if your signal flipping bits correctly, or if there is or any delays or jitter. Measurements when data is transmitted can be interpreted wrong on receiving end. So bits are getting correct or not, we will check. And we opened an eye diagram, we'll get two custom measurements. We can set it that amplitude, and we'll get some histograms readings. So we can set it using the oscilloscope options of bit rate measurement and clock recovery. If you have oscilloscope only, it will be easy to explain that, because the options will be present in the oscilloscope, right? We have to see and we have to set the eye diagram. We'll be having eye diagram options on this oscilloscope, like bit error rate we need to measure, and using that bit rate measurement. First, we will be seeing the bit rate measurement. Using that bit rate measurement, we will be going to clock recovery, and using that clock recovery, we will be setting that amplitude of the eye, width of that eye. After setting the eye diagram and the color complexes on the oscilloscope, if we run that CMM script, we will see the eye diagram. So it is having certain process to construct this eye diagram. Using the options on the oscilloscope buttons only we can do that oscilloscope construction. It is like bit complex. They won't ask that much, but once they'll give you the oscilloscope, then only you can understand how to construct that all eye diagram. Basically, you can tell in interviews like you can set up an eye diagram using the bit rate measurement and clock recovery.
Okay.
Bit measurement and clock recovery. Using that, we can set up an eye diagram in an oscilloscope. In modern oscilloscopes, we have directly one button like eye diagram button. Here, by clicking that, we have some measurements like what will be the width and amplitude to select. Based on that, like for amplitude, which color you have to use, for width, which color you have to use. Based on that color complexity, we'll be seeing eye diagram colors like yellow, pink, different colors. With different colors will tell us different measurements like height, width, like that. Basically, they'll ask basic of only in eye diagram because it's for high speed eyepiece. For initial stages, you will be given only low speed eyepiece like I2C SPI using that Prodigy or previous tool. Previous tool is like protocol validation suite. Using the two equipment, you will be checking that protocol is working fine or not. Any doubt in this?
So mostly which oscilloscope will be used in the industry?
25 gigahertz of bandwidth oscilloscope. Keysight. Because the oscilloscope can accumulate low speed and high speed eyepiece, right? 25
Yeah.
gigahertz of bandwidth oscilloscope is too high. That can be used for low speed eyepiece like I2C SPI JTAG and high speed eyepiece like PCI, SGMII, Aurora. So in industry standard point of view, they'll use 25 gigahertz of oscilloscope.
Okay. Thanks.
Like any other doubts? Any other doubts? You want me to explain any other protocol or any other thing you want to know? Basically, mostly they'll ask that oscilloscope question and how you're making that master-slave communication or slave-to-master communication, how you'll use the thermostream. Okay, once recall everything, if you have any doubts, I'll clarify and I'll move to the next topic.
Hello.
Yeah.
Yeah, actually, I have a doubt. Like, if I use a high bandwidth oscilloscope and I connect with low speed peripherals, so the sampling rate will be different, right? So, how can I configure that in oscilloscope? Like, how can I check that in high bandwidth oscilloscopes? What are the changes should I do?
Like there is no need to do any changes basically. If you connect it right, you can automatically see the signals. You're saying you're having low speed IP and you're wanted to see it in high bandwidth oscilloscope, right?
Yeah.
Yeah, then there won't be any effect. Like there won't be any effect with the signal. So it's good
Okay.
to take the sampling of that signal.
Okay.
But for in
Yeah.
same case, if you reverse it, right, for high speed IPs, if you use low speed bandwidth, low bandwidth oscilloscope, then it will be difficult to see that signal.
Okay. Yeah.
Yeah. Any other
Right.
doubts? Any IP level of doubts? Basically, in IP level of validation, you should understand first what is the clock frequency or signal of that IP, then data rate, and later you have to understand how can we do that setup of that validation. Validation of that, how we have to do that setup, that things you should understand. Any doubts in previous slides?
If you have some time, could you cover the starting topics? I have missed the class. I mean,
Yeah,
I just
sure.
arrived a few minutes
Yeah,
later.
sure. Like up to which slide you have listened so
I
that
think
I.
it's the oscilloscope and the pictures of the probes, I guess.
Okay, like the from there only I think today class started, right? From the
Oh,
cables and the oscilloscope, the class started. Like before that, yesterday class, like introduction to post silicon validation, and how will be we are doing the PVT characterization. That is very important topic. Like PVT characterization initially for the pressures and for
yeah, I
with less
listened the yesterday class, but
hmm.
yeah, today I think I missed the first two slides of it.
Okay, I'll explain the first two
Yeah.
slides. Yeah. Is it visible now? Yeah. You're saying from this slide, maybe, right? Test
Yes, yes.
cables, yeah. We'll be having different types of cables. In college days, we'll use the lab like analog electronics, digital electronics, right? At that time, and you'll be doing some lab for Arduinos, how like microcontrollers, how to use, how to build applications, and at that time will be seeing different cables, right? That male to male, female to female cables that are nothing but a Burke cables. So like the different cables are there in industry to connect that validation setup. So they will be having different cables and different probes. Why we have to use cables means different cables and different probes means different signals will have the different frequency handling capabilities. So if you select the wrong cable, right, it will distort distort the signal and noise will add into that signal, and we'll be taking the incorrect or wrong measurements. So we always have to keep in mind like we have to use the correct cables and correct probes, because this will affect the signal if you are using the wrong cables or wrong probes. So for you people to understand how it will look, I have attached this. Like banana cables is nothing but we'll be using for power supplies. The end of the cable will be looking like this, 4 mm plug like that. It will be like this type, right? Black and red and black color. Banana cable end will be like this, and Burke cables will be one side pinned, and another side will be like this, male to male, female to female, like that we'll be seeing in lab, right? So, and in bullseye cable, it will be seeing like this, and we'll be having bullseye pin as well to screw and unscrew. It will be having BNC. BNC cables, we generally see this type of things for oscilloscope. Oscilloscope will be connect, right? For oscilloscope connection, we'll use this BNC cable. And we'll be having SMA cable. SMA cables, we'll use for vector network analyzer and other sort of connections, we'll use this SMA. So basically for low speed IPs, we'll use BNA cable connection. For high speed IPs, we'll use bullseye. So this is one type of validation setup, how to connect which probe, like that. Here oscilloscope is mainly having two probes. One is passive probe, which are used for low speed signals like I2C validation, SPI validation. For high speed, like high speed, right? For high speed, we'll use differential probe. Differential probes will use like this. Differential probes will be having differential signal type and its bandwidth is gigahertz. If we see the comparison of that passive and differential, right? In passive probes, the signal is single-ended. In differential, the signal is differential. In bandwidth, in passive probes, it is up to 300 megahertz. But in the differential, it will go to some several gigahertz. And input capacitance will be higher in passive probes. In input capacitance will be low in differential probe. And input impedance is 1 mega ohm. And in differential, it is higher. And loading effect is higher. And in passive and differential probes, loading effect is very low. Generally, it is passive probes are used for low speed IPs like I2C, SPI, UART. For differential probes, we will be using for high speed like USB, PCI, Aurora, SGMII, all these others IPs like serialization, deserialization IPs. High speed IPs will use differential probe. Banana cable is used for DC and low frequency signals. It is for simple plug and play. Like it's like plugging that power, like power supply. One end of the BNA cable is connected to power supply, another end will be connected to DUT. No impedance control in the banana cable, and it in application wise it is used for power supply connections and basic measurements. Burr cable is used for multi-pin connector. With that, we can connect to I2C, SPI, like that. It is used for JTAG digital interfaces like JTAG, GPIO, and it is used for debugging logic connections inside boards. And bullseye is like one type of bullseye cable will look like this actually. It will be like this, very thin, and it will be having some sort of gap in between this cable top connector. Why we'll be having that cable top space means we'll be having one type of small screw. In our home, we'll be having some screwdriver, right? Same like that, we'll be having bullseye connector pin. So to screw that on the DUT, for example, this is your DUT validation board. Here you will be having SOC. Somewhere around here you will be having bullseye bullseye port. Bullseye port will be there. It will be having 8 pins, 1, 2, like that. It will be having 8 pins side by side. So we'll be seeing bullseye is for high speed, right? High speed signals will be TXP and N, RXP, and N. So we'll be connecting the TX pin. For example, we'll be keeping the cable here inside. And using this pin, right? Using this bullseye pin, screw type, we will screw that cable inside this bullseye port so that it will be sticked here. So another end we will connect that to oscilloscope. Differential probe will be there with golden tips. With that, we'll connect to oscilloscope. We'll connect to the oscilloscope. When we run that CMM script in the trace32, we will see the tie diagram in this thing. So bullseye is used for high speed, and BNC cable is used for connecting to the oscilloscope, where it is a coaxial cable, and it with a controlled impedance of 50 ohms. So if it is impedance is not matching, that cable is having some impedance. If the cable impedance and system impedance are not matching, then we will see some reflections, signal reflections and signal distortion and noise in the signal. So we should always we should always make sure that cable impedance should match with the system impedance. It is good shielding, and it is used for oscilloscope connection. Medium to high frequency signals, we use this BNC cable. Coming to the SMA cable, it is a precise RF connector and high frequency it is having. And in use case type, it is used for vector network analyzer, like that. And coming to the oscilloscope probe, we'll be having the passive probe and differential probe. Passive probes are nothing but it will be like having one end pin type in one end. In oscilloscope, just we need to pin it on oscilloscope. But differential probes will be having golden tips in another end. So in oscilloscope, we'll be connecting that golden tip to the oscilloscope here. So in passive probe, it is used for low speed IPs. So direct probe will be there, no amplification is required. And typically attenuation rate will be 1x to 10x, and bandwidth is 100 to 300 megahertz. And characteristics are it is having high capacitance, more loading on a signal. It is for low speed IPs like I2C, SPI, GPIO. And differential probe is like high speed. It is used for high speed IPs like SGMII, Aurora, PCI, USB, LVDS, DDR. It measures the difference between two signals and is used for differential signaling. So why we use this differential means it will reduce the noise, EMI effect. It is having because it is having the low capacitance, high bandwidth, gigahertz range, and it is having high CMRR, noise rejection rate. So we'll use for low speed passive probe, high speed IPs, we'll use differential probe. Yeah, I think now with the first two slides of test cables and oscilloscope probes are clear, right?
Yes,
Hello?
it's
Yeah. Coming to the another validation lab tool is power supply. So in our analog electronics, digital electronics, we'll be using this power supply with breadboard, right? Same way in lab setup also, we will use little bigger power supplies, but use case and how to use that power supply is almost similar, same. So in every SOC needs the voltage to check it function correct or not, right? We'll be having a 3-channel power supply, 2 channels, multi-channel power supplies will be having. So like we'll be having one core voltage VDD voltage sweeps to test the timing margins, and we'll be having the input output rail for stable communication of interfaces like SPI I2C, DDR, PCI IPs, and analog rail, power rail, PLLs, SARDAs, and sensitive analog blocks for clean signals. Why it matters means PV, It enables the PVT characterization like process, voltage, temperature, and IP validation. In PVT, if we see, we'll be giving different voltages, right? The different voltages are given using this power supplies only. And in IP level of validation also, we'll be setting that voltages. It supports the stress testing and across voltage corners. It is power delivery for debug and compliance checking. We'll use that power supply. And we'll be having an 4-wire connection and 2-wire connection. 4 wires are nothing but we'll be having an extra sense wires. In normal 2-wire system is we'll be having positive and negative like VDD and ground, red wire and black wire. In 4-wire system we'll be having additional sense wires with green color wires. So without sense wires voltage drop occurs for long cables. So that DUT will not receive the exact voltage we set in the power supply. So we'll use for that accurate measurement and precise control, we will use 4-wire system. 2 extra sense wire will be there. The voltage is directly at the load, compensating the cable drop. There won't be any cable drop then. There won't be any cable resistance. So whatever the voltage we set in the in power supply, we can get the same voltage, precise voltage on the DUT, SOC, validation board. So for 4-wire system, 4-wire connection, backside of the power supply, we will connect that 4-wire system. For example, it's an power supply. It is having channel 1, 2, 2 and 3. So we'll be setting some 0.9, 1.8, 3.3 voltages. So inside we'll be having 2 terminals. One is VDD and another one is ground. This one will be red wire and this one will be black wire. It is 2-wire connection. Like directly we will take these 2 wires and connect to the validation board. Here it will be having SOC. So directly we'll be connecting where that 0.9 is required on the board, we'll connect. So back of this power supply, we'll be having another 2 wires, which are like sense wires. So, we'll connect that sense wire. We need an accurate voltage at the load. And this is one visualization purpose. I have taken this image like power supply. 3-channel power supply means it will be having channel 1, channel 2, channel 3. And in that we'll be having one core voltage, which will be deciding how that interface main voltage will work like that. And coming to the companies, right? Keysight 6N6700 series 3-channel power supply will be used, and R&S power supply is there. Tektronix power supply is there. Next, we will be going to see the Thermostream. Thermostream like mostly used for PVT characterization. PVT characterization of any SOC or any transistor. We'll use that PVT. Like we'll see when we give the temperature, how that silicon or how the transistor is behaving. So Thermostream, basically we use Temptronics Thermostream, and it is used for precise temperature sourcing on the SOC during the PVT characterization by cycling devices for across the extreme temperatures from normal, cold and hot, because we'll keep cold first then hot, because in cold temperatures we'll see the ice formation. So ice formation will in terms give some water droplets on the board, validation board or SOC, so which will reduce the performance, or sometimes it will cause some damage. So that's why after that cold temperature, running on cold temperature, we'll directly keep the temperature to the hot temperature. And why temperature matters means mobility of that carrier and electrons will be at high temperatures, the electron mobility will decrease. So it will be having lower switching and timing failures. And coming to the leakage current, it increases exponentially with temperature. When temperature is increasing, right, the leakage current will be more and higher power consumption and possible logic errors. And threshold voltage, the voltage drops as temperature increases. So transistors turn on more easily. So affecting the noise margin. So we see some noise margins. Jitter and ISA, thermal variations will distort the transitions. So I diagram will horizontally shrink. Noise margin means it will at extreme conditions we'll see the reduced noise margin. So risk of bit error. So vertically also that I diagram will change. So in automotive SOCs, there will be some different ranges of these temperatures. Like in automotive SOC, we are validating across -40, 150, like -40, -20, -10, and 10 degrees, 20, 50 degrees, 80 degrees, 100, 130, and 150. Like that, we will vary the temperatures to see the silicon behavior or transistor. And we will use some mobile SOC, means we will testing from 0 degrees to 85. And industrial chip means we'll use from -150 to 150, -55 to 150. And sensor or data center devices means it will be 10 to 90 degrees Celsius. And high-end Temptronics systems means, but maximum Thermostream also having some limits. Beyond that 225, we can't source that temperature. And it provides, why it is essential in PVT means, it provides a direct temperature sourcing on SOC package. And we have to see voltage variations as well. We'll be having some thermal cap, and backside of that air pressure we have to check, because if we are not giving the correct air pressure, we are not going to get the correct temperature on the SOC. And we have to see whether that SOC is getting the set temperature. For example, if we set 50 degrees and we are getting a doubt like we are not getting 50 degrees. To ensure that correctness, we will use any thermocouple or any temperature sensors there to see whether we are getting the correct temperature as we set it on the Thermostream. Like if we connect Thermostream, this is how our setup will look. Like this is the 3-channel power supply. This will be our validation board. This will be our SOC with socket, and we'll be having Thermostream device. So this will be some orange color sponge, and this will be a thermal cap or hood, we'll say. We'll keep that in center. We'll be having SOC. We'll cut that sponge in such a way that we have to keep the thermal cap sourcing the temperature on SOC. Once we set this setup, right, we'll set the temperature, we'll set the voltage, and we will run using the trace 32, and we'll see the corresponding signals here. This is how that overall Thermostream will look like. It is like by touch only we can set that readings, like hot temperature, ambient temperature, cold temperature. Using this thermal cap or hood, we are making that head of the Thermostream down or up. Yeah, any doubts in this, like any doubts in power supply? In power supply, we'll be having store and recall measurements, where we can store one particular set of readings like voltages and how much current. For safeguard, we'll keep the current limit as well and voltages. We can store and recall that settings. Any doubts as of now? And in power supply, we'll be having constant current and constant voltage modes. In constant current mode, it holds output current fixed and voltage drop raises to maintain that current. And in the constant voltage mode, it holds that output voltage fixed and current changes based on the load.
So can we change the voltage settings through power supply also without having help with the system? Like we usually set it through BIOS, right? Sometimes, but can we change the voltage of it through power supply too, like for SOC?
If you want to change the voltages, right, you have to go near the key site power supply and we have to change. If it is an automation, right, we can change it from our system using that
Okay.
LabVIEW NI visa. We'll be having one driver NI visa. Using that string, we can control that power supply. If it's an Python automation, we'll use Py visa to control that power supply. We can do manually as well as in automation, like we're using the system also, we can control that power supply.
Okay.
Yeah. Any other doubts? For safeguarding, we will use CC mode. In power supply, we'll be having CC mode, CV mode, constant voltage, constant current mode. And we'll be having some buttons like store and recall to store that repeated values. And we can recall that readings whenever we need that voltages. Some common power supply models and how many channels it will be used, for which use case we'll use. Thermostream. Any doubts here? Any slide if you want me to explain, like any topic?
Could you explain more detailed on this thermal thing? Like there's a thermal, like you told, there's a picture at this one, yeah.
Mhm. Yeah. So overall, the thermostream equipment will look like this. So at this end, if you see, right, I think my uh, mouse is pointer is coming, right? Yeah. This is the main thing. It is called thermal handling. Like head will be there, right? We can position this using it here. Two arrow marks will be there, right? Up arrow and down arrow. So if you click the down arrow, this uh this handle will come down. So by using the down arrow button, we'll make this head down, head of the thermostat down, like this. So here we will be setting some temperature like 50 degrees, 60 degrees, 70 degrees. Using this sponge will be there, right? We can't directly keep that thermocap on the validation board. We'll use some thermal sponge here for safety. And we will be placing the thermal cap on the sponge. And in center of this, right, you will be having the SOC. To see that SOC behavior, we are sourcing some temperature on the SOC to see that SOC behavior. Like at minus 10 degrees, how that SOC behaves. At minus 40, how it will behave. And 50 degrees, how it behave. 150 degrees, how it will behave. For that, we'll use this thermostream in short.
Okay, for decreasing the temperature also, do we use this one?
Yeah, we can use for low temperatures and cold temperatures and hot temperatures.
Okay.
Any other doubts you have? Any IP, any signal, how to see? Anything you want me to explain, setup, or you have any doubts in IP level, EVT or cables, probes? And mainly what we'll do is, for oscilloscope probes, we'll do calibration as well. To make sure for every validation before, we'll use the calibration. For the passive probes, we'll be using some pin type will be there. We'll be connecting and we will be rotating the pin to make sure it signal is not having any noise like that. For differential probes, we will use calibration kit. Backside of oscilloscope, we'll be having some kit in of calibration. We'll keep that in calibration mode, oscilloscope, and we're going to do that calibration of active probes. Calibration. And in oscilloscope, we'll be having one trigger option to see that waveform in one window. We have to use the trigger option. We'll be having auto scale, and we'll be having clear and vertically movement of that signal. Horizontally we can move that signal. We'll have that pen drive scope of to uh, take that waveform reading. Basically, for any IP, you should know how to do the schematic, board schematic, and how to do the connection, how to run that test case, execution of the test case, how to use this power supply, how to use that oscilloscope. And there will be some other equipment like DMM, SMU, vector network analyzer, source measure unit, and digital multimeters. That equipments and other concepts I'll cover it in next classes. So do you have any doubts in this? Like, want me to explain anything? Like how the career will be in post-silicon validation, or what should we learn more? Which sort of companies will take post-silicon validation engineers? Do you want me to explain anything in career perspective? I can explain you. Or if you want me to tell on this concept also, I can explain.
Yeah, what are the main topics or the main topics that the post like to get into a post silicon validation role? So, what are the key topics that we should have knowledge? Like, we should have this must be done or should know about this particular topic like that?
Silicon validation, you should know the instrument handling, like hardware instrument handling. Like there will be some multiple hardware instruments. Basically, for basic point of view, you should know how to use power supply, how to use the DMM, how to use the signal generator, how to use that source measure unit SMU, how to use the oscilloscope. Thermostream and other things are industry standard point of view, but basically basic hardware equipment how to use you have to know. And second thing, you should know how to see the schematic of any board or any IP. And you should know basic understanding of protocols if it is an IP level of validation for digital IPs, low speed or high speed. If it's their analog IPs means it is different. Analog IPs means there will be PLL and ADC like that. So like in IP wise, if you given any IP, you should know that IP level of understanding. What is the clock frequency of that clock frequency of that IP? What is that data rates and how that validation setup will look like? IP level of validation and hardware tools how to use. You should understand that, and you should know any programming language like C or LabVIEW or Python. Mostly they will prefer LabVIEW and C or LabVIEW and Python. That is enough. Like yeah, if you have this much understanding, right, it will be good, and you should know how to execute it. Initially, they won't give you development side, like to develop any test case or to do anything from scratch. They will give you test case, but you have to able to do that execution, how to bring this setup, how to do the setup, how to do that validation.
And also, can I get overview on like what is logic analyzer? I mean, I heard
Yeah,
it multiple times, but I have no idea.
okay. Logic analyzer is basically used to analyze that logic for IPs, right? We'll be having different IPs here. So to analyze that logic, we'll use some logic analyzer. And like what will be, how it will, the logic is there. To analyze that, we'll use that logic analyzer. Like Prodigy is also one type of logic analyzer. We'll be setting it as master mode or slave mode, right? And we'll be doing that logic to capture that and display the digital signals. We'll use that logic analyzer. Prodigy and PVS tool are one type of logic analyzers only.
Okay, thanks.
Oh. Any other doubt? Prodigy are PC based logic analyzer to analyze the logic, to analyze that waveform, to analyze that capture of displays the digital signal. We'll use that Prodigy as master, as Prodigy, slave as DUT, and as well as we can use slave SOC as master and slave as Prodigy. That are basically to analyze the functionality. To check the correctness of logic of any IP, we'll use that logic analyzers. Any other doubt? Any other IP to be understood, like UART? I think you all know about UART, USB, right? Other IPs, right?
Yeah, but can we know like how will we validate USB for like this JTAG and all?
Yeah. USB also similar only. Same like how we do high speed validation, right? Same way, we'll be having onboard USB port. So we'll be connecting that USB port signal probes to oscilloscope, and we'll be using a power supply, and we will be running that script of USB, and we will be seeing the I diagram. In the specification document, we will be given that USB, what is will be the raise time, fall time, setup time, hold time, skew rate. Everything will be mentioned in uh, that specification document. We will compare that I diagram results with that specification. If that specification is matching, right, then the test case is passed. If specification is not matching with the output we got, then we can say that is failing. That test case is failed. Yeah, basically all IPs validation is similar. Like if it's a low speed IPs means we will use Prodigy or PVS, protocol validation suite. If it is a high speed IPs, we will directly connect that using schematic. We will see where that PCB IP is present in the validation board. We will connect that signals probe. We'll probe that signals to oscilloscope, and we will run that USB CMM script in the trace 32, and we will see that I diagram using the specification document given. We will be verifying whether our results are correct or not. If our result and the specification document is matching, then we can say the test case is passed. If it is not matching, we will see that test case is failed, and we'll do some failure analysis, root cause analysis, failure analysis, why it is failing, what we need to change, any board reworks we have to do. If you given any new speed IP, right, like new IP for validation, you don't know anything about that IP, then what you have to do is your approach should be like, what is the latest that IP data rate, what is the latest version of that USB, what is that data rate, what is the clock frequency of that IP, like that we should know, and we have to set that things, and we can validate. Same like SGMII Aurora, we can do the USB validation also. Any other doubts?
Like for high speed protocols, so if we wanted to, like you told that for low speed we use Prodigy and PVS, right? So without using those tools, where we connect to SOC, like for high speed ones?
You are asking for high speed, where we connect
Yeah, we don't use Prodigy,
G and
Prodigy.
previous tool, yes.
Yeah, then where do we connect the like where do we connect it
Like for example,
without
I'll
the
explain like for SGMI and Aurora. SGMI and Aurora both will have bullseye port here with 8 pin. So that 8 pins, right? 8 pins will be having TXP, TXN, RXP, RXN. Same in USB also will be having the same pins. Any differential high speed protocols having the same signals like TXP, TXN. And it means transmit positive, transmit negative, like TX positive, TX negative, PX RX positive, RX negative. We will take that signals, right? 4 signals, and we'll probe it to oscilloscope. This is for example, this port is for SGMII. This port will be for Aurora in validation board. Here it will be having some USB port. USB port. Here, like any USB port is there, right? Like USB port. You'll be having some other PCI port. You'll be having some DDR. Everything will be on this validation board only. Like some ports will be there. We'll insert the SOC, and we will connect that ports to oscilloscope. 4 channels of oscilloscope. If it is TX means we'll connect to TXP, TXN. If it is RX means it will connect to RXP, RXN. Why we'll have that differential pair of signal means it will reduce the noise EMI effect. So we'll be having the differential signals for high speed. We'll connect that high speed signals to oscilloscope. On the board itself, we'll be having some ports like where to connect I2C, where to connect SGMII, where to connect Aurora. That everything will be given by board team. Schematic will be given. By understanding the schematic, we can do that validation.
Yeah, got it, ma'am. Thanks.
Yeah, thank you. I think we can conclude it now. Thanks for joining.